That first iconic image of a black hole revealed a cosmic monster. But what if that shadow is not a pit of destruction, but a doorway to a new reality? We are about to explore 25 theories that turn everything we think we know about black holes upside down. You will discover how these cosmic puzzles might hold the keys to wormholes, new universes, and the fundamental laws of all existence. We will investigate if information can truly be lost forever, and what bizarre forms of matter might lurk within. Which of these mind-bending possibilities makes you question the very nature of reality itself? The shadow at a black hole's heart may not be a final destination. It could be the mouth of a cosmic tunnel, a wormhole threading through the fabric of reality to another place and time. This idea emerges directly from Einstein's own equations of gravity, which describe spacetime as a flexible sheet that can bend, warp, and even stitch itself together. The theoretical bridge connecting two distant points is known as an Einstein-Rosen bridge. Picture it not as a hollow pipe, but as a throat of warped spacetime, a shortcut linking a black hole here to a theoretical white hole elsewhere. A white hole would be the opposite of its dark twin, violently expelling matter and energy rather than drawing it in, potentially into another universe entirely. So instead of a one-way trip to oblivion, falling into a black hole could be a journey to a distant galaxy or a completely different cosmos. The problem is that the classic wormhole is fantastically unstable. According to general relativity, the tunnel would pinch shut the instant it formed, collapsing faster than the speed of light. Anything entering would be crushed long before it could reach the other side. Yet there is a tantalizing possibility. Some physicists speculate that strange quantum forces, effects we do not yet fully understand, could act as a sort of cosmic scaffolding. Exotic matter with negative energy density might prop the wormhole open, creating a stable passage through the abyss. This remains entirely theoretical, a ghost in the mathematics, but it suggests that the universe might be far more interconnected than we ever dreamed. But if wormholes offer a potential escape from a black hole, Stephen Hawking proposed a different kind of leak entirely. His work revealed that black holes are not entirely black. They can, in fact, evaporate and vanish over eons. This slow death is driven by a bizarre quantum process right at the precipice of the event horizon. In the seething vacuum of space, pairs of virtual particles constantly flicker in and out of existence. Normally, they annihilate each other almost instantly. But at the edge of a black hole, one particle can fall in while its partner escapes. The escaped particle becomes real, stealing a tiny bit of the black hole's energy to do so. This slow, steady trickle of escaping energy is Hawking radiation. Over unimaginable timescales, this process causes the black hole to lose mass, shrink, and ultimately, in theory, disappear. This solved one puzzle but created a far greater one, the infamous information paradox. In quantum mechanics, information is never truly lost. If you burn a book, every single letter and word is, in principle, recoverable from the smoke and ashes. But if a black hole evaporates, what happens to all the information about the things that fell in? Every atom, every particle, the complete history of what was consumed. Hawking's original work suggested it was erased from the universe forever, a fundamental violation of quantum law that threatened to unravel our understanding of physics. This paradox forced scientists to confront a radical idea. Perhaps the information is not lost inside the black hole, but is instead preserved on its surface. The event horizon could act like a vast cosmic hard drive, encoding every bit of information about what falls in onto a two-dimensional holographic film. In this view, the three-dimensional reality we perceive inside could be a projection from the information stored on that two-dimensional boundary. So when the black hole radiates, it is not destroying information, it is slowly and chaotically reprinting it back into the universe. This holographic principle suggests that our own reality might be a projection from a distant two-dimensional surface, a concept that redefines the very nature of existence. This holographic encoding on the event horizon leads to a conclusion so strange it challenges our perception of reality itself. If all the information about a three-dimensional star is perfectly stored on a two-dimensional surface, then our own rich, three-dimensional universe might also be a hologram, a magnificent projection from data stored on some distant two-dimensional boundary. This is the core of the holographic principle, an idea born from the mathematics of string theory. Think of it like a credit card hologram. The flat, shiny surface holds all the information needed to create the illusion of a three-dimensional image. In the same way, the event horizon could hold all the information about the black hole's interior, and by extension, our entire cosmos might be a similar, grander projection. This solves the information paradox in a breathtaking way. Information is never lost inside the black hole because it never actually falls in. Instead, it is smeared and stored like a cosmic tattoo across the horizon's surface. But this creates another deeply personal paradox. What happens to you if you fall in? According to black hole complementarity, the answer depends entirely on who is watching. From the perspective of an outside observer, you would never actually cross the event horizon. Due to the extreme gravitational time dilation, your approach would appear to slow to a frozen halt. Your image would redshift into invisibility as you are vaporized by Hawking radiation, your information encoded onto the shimmering surface. But from your own perspective, nothing special happens at the horizon. You would cross it seamlessly, following the laws of physics as you know them, embarking on your journey into the black hole's mysterious interior. So which story is true? The incredible answer is both. The universe, in its most profound weirdness, allows for two contradictory realities to be true simultaneously. You are both incinerated on the boundary and passing through it unharmed. The information about you is both scrambled on the surface and preserved within the interior. This is not a flaw in the theory, but a fundamental feature of a quantum universe where reality is not absolute but is shaped by what we can measure. It resolves the information paradox by stating that no single observer ever sees the information get destroyed. This same holographic principle might even explain the universe's greatest ghost. For decades, we have known that most of the matter in the cosmos is invisible, a mysterious substance we call dark matter. Its gravitational pull holds galaxies together, yet it emits no light and has never been directly seen. What if the solution to this cosmic riddle has been hiding in the densest objects of all? The answer could be primordial black holes. Unlike the stellar black holes formed from collapsing stars, these would be ancient relics, born in the frantic, seething conditions of the Big Bang's first second. In that incredibly dense and hot early universe, pockets of matter could have collapsed directly into black holes of almost any size. While most theories focus on black holes many times the mass of our Sun, the primordial kind could be far smaller and far more numerous. Some might be as massive as a planet, while others could be no larger than a pebble or even an atom. These tiny, ancient black holes would be the perfect candidate for dark matter. They do not glow like stars, they are far too compact to see directly, and they would be scattered throughout the cosmos, weaving an invisible gravitational web that perfectly explains why galaxies spin the way they do and how the largest cosmic structures formed. Finding them, however, is the ultimate challenge. You cannot see a pebble-sized black hole floating in the void of interstellar space, so astronomers hunt for them indirectly using a cosmic phenomenon called microlensing. Imagine a tiny, invisible black hole drifting between us and a distant star. As it passes through our line of sight, its immense gravity will act like a lens, bending and focusing the star's light. For a brief moment, that star will appear to brighten dramatically, then fade back to normal as the black hole moves on. These fleeting flashes in the night sky are the telltale signatures of a hidden population of dark matter black holes. If this hypothesis is correct, it would be a monumental discovery. It would solve the 80-year-old mystery of dark matter in one bold stroke, revealing that it was made of black holes all along. More profoundly, it would give us a direct window into the universe's very first moments. Each primordial black hole would be a frozen fossil from the Big Bang, a time capsule holding secrets about the forces that shaped reality at its birth. The invisible fabric of our cosmos might be threaded with countless cosmic ghosts, and their silent gravity could be the only thing holding our galaxy together. Yet this elegant solution of two realities comes at a terrifying price. To preserve the sanctity of information for an outside observer, the interior of the black hole might have to become a place of pure violence. This is the firewall paradox, a concept so radical it suggests that the event horizon is not a smooth gateway, but a blazing wall of fire. The paradox begins with a fundamental conflict between two cornerstones of physics. Einstein's equivalence principle states that a free-falling observer should feel nothing special when crossing the event horizon. For you falling in, it should be a non-event, a seamless passage into the unknown. But quantum mechanics demands that information must be preserved, encoded on the horizon's surface. To prevent any information from being duplicated, a violation of quantum rules, the two versions of you must be kept separate. The you that is vaporized on the surface and the you that falls in cannot both be real. The firewall is the universe's brutal solution to this problem. It proposes that just inside the event horizon lies a literal curtain of unimaginably high energy particles. Any object crossing the boundary would be instantly and completely incinerated. This firewall protects quantum mechanics by ensuring that only one version of events is real. You are not both inside and outside, you are simply destroyed. This idea has sparked one of the most intense debates in modern theoretical physics. It forces a choice between two cherished principles. Do we abandon Einstein's elegant idea that you can fall through the horizon without noticing, or do we rewrite the rules of quantum information? The very laws of physics seem to be at war with themselves over the nature of this ultimate boundary. A firewall means the black hole is not a tunnel, but a cosmic crematorium, its interior a realm of fundamental contradiction. This firewall paradox forces us to ask what is truly happening to all that information. Perhaps it is not being destroyed but processed. The event horizon, with its holographic storage of quantum bits, could be acting as the universe's most powerful and complex computer. Each bit of information that falls in, every particle and its properties, becomes a qubit on this cosmic sphere. Unlike a standard computer bit that is either a 1 or a 0, a quantum bit can be both at once, a state of superposition that allows for exponentially more powerful calculations. The chaotic churning and entanglement of these trillions upon trillions of qubits could be performing a computation of unimaginable scale. What could such a cosmic processor possibly be calculating? It might be running the ultimate simulation, computing the very evolution of spacetime within its domain. The fabric of reality inside the black hole might not be a fixed stage but a dynamic output, generated in real time by the frantic processing on the boundary. This idea transforms the black hole from a simple gravitational pit into an active, thinking entity of sorts, a natural engine of information processing that could be fundamental to how the cosmos operates. If consciousness itself arises from complex computation in our brains, then what kind of awareness might emerge from a system with the entire history of fallen stars encoded on its surface? While we should not anthropomorphize a black hole, the sheer scale of its information processing hints that the universe might be capable of forms of intelligence far beyond our comprehension. This suggests that the laws of physics we observe may not be fundamental rules, but rather the stable, user-friendly interface of a deeper, computational reality running in the background of the cosmos. But the firewall is only a paradox if the event horizon exists at all. What if the most dangerous part of a black hole, its central singularity, was not hidden from view? The cosmic censorship hypothesis is a fundamental, though unproven, rule in physics that states all singularities must be clothed, veiled behind an event horizon. This is a cosmic safety mechanism, protecting the rest of the universe from the infinite, physics-breaking chaos at a black hole's core. Yet some equations suggest this censorship can fail. A naked singularity is a point of infinite density that is completely exposed to the universe, an infinite tear in the fabric of spacetime with no event horizon to shield us from its consequences. How could such a thing form? The most likely candidate is a black hole spinning at the absolute maximum possible rate. Most black holes are thought to be Kerr black holes, which possess not just mass but immense rotational energy. This spin flattens the black hole into a squashed sphere and drags the very fabric of spacetime around with it. If such a black hole were to spin fast enough, the mathematical models show that the event horizon could simply vanish like a bubble popping, leaving the raw singularity naked for all to see. The moment it is exposed, our understanding of reality would shatter. The laws of physics, which depend on a smooth, predictable progression of cause and effect, would break down completely at the singularity's boundary. In its presence, you could theoretically travel backwards in time. A naked singularity would not just allow for time travel, it would force it upon the region of space around it, creating closed time-like curves. This is a path through spacetime that loops back on itself, allowing an object to return to its own past. Imagine firing a probe toward a naked singularity. Instead of being destroyed, the probe could follow a trajectory that brings it back to a point before it was ever launched. This is a causality violation, the ultimate scientific paradox. If you could go back and prevent your own launch, how could you have traveled back in the first place? The universe would be plunged into a state of logical inconsistency where effects could precede their causes. Finding a naked singularity would be the most profound discovery in the history of science, but it would also be the most terrifying, revealing a cosmos where the fundamental rules of existence are not just unknown, but potentially absent altogether. The violent death of a star does not always create a simple black hole or neutron star. There might exist a shadowy population of objects caught in the forbidden zone between life and ultimate destruction. Astronomers have long observed a strange cosmic boundary known as the mass gap. The heaviest neutron stars cannot exceed about 2.5 times the mass of our Sun. Beyond that, gravity overcomes the quantum forces holding the star apart, and it collapses into a black hole. Yet the lightest black holes we have found are at least 5 solar masses. This leaves a mysterious gap between 2 and 5 solar masses, a range where almost nothing has been observed. Why does this void exist? The answer might be that our categories are wrong. Some objects we have classified as neutron stars could be something else entirely, low-mass black holes or bizarre hybrid objects born from unusual stellar deaths. When two dense objects spiral together and merge, they send ripples through spacetime called gravitational waves. Our observatories are now listening for these cosmic tremors, and the signals from mergers in the mass gap could reveal the true nature of these borderline entities. A collision might not be between two neutron stars, but between a neutron star and a tiny black hole, an event that would tear the star apart in a spectacular flash of light and gravitational energy. The internal structure of such a hybrid object would be unlike anything we know. A typical neutron star is so dense that protons and electrons are crushed together, forming a sphere of pure neutrons. But in an object at the upper limit of stability, the pressure could be enough to crush the neutrons themselves. They would dissolve into a soup of their constituent parts, quarks and gluons. This is a quark-gluon plasma, a state of matter that has not existed freely since the first microseconds after the Big Bang. It is a liquid of pure fundamental forces, a fleeting, perfect state that might be permanently trapped inside these cosmic missing links. Finding an object in the mass gap would do more than just fill a blank spot in our charts. It would force us to rewrite the textbook on stellar evolution, revealing a whole new class of celestial bodies that defy our clean classifications. The universe may be hiding its most exotic forms of matter not in the hearts of giant black holes, but in these smaller, quieter, and far stranger objects. If black holes are the universe's ultimate drains, then white holes are its mythical fountains. They are the exact theoretical opposite, a region of spacetime from which matter and energy can only pour outward, never be absorbed. In the elegant language of mathematics, a white hole is simply a black hole running backwards in time. Where a black hole's event horizon is a point of no return, a white hole's boundary would be a point of no entry. Anything approaching would be violently repelled by an unimaginable outflow. This is not a place you could ever visit, only a cosmic source you could observe from a safe distance. The connection between these two extremes is more than just mathematical poetry. Some solutions to Einstein's equations suggest that the interior of a black hole might not end in a crushing singularity, but could instead be bridged to a white hole in a separate universe. This transforms the entire system into a wormhole, a cosmic recycler that takes matter and energy from one cosmos and expels it into another. Imagine our universe as one leaf on a vast, growing tree. A black hole here could be the root that draws in material, channeling it through a cosmic stem to burst forth as a new universe from a white hole on another leaf entirely. This offers a breathtaking possibility for the origin of everything we see. Our own Big Bang, with its sudden, immense eruption of energy and matter, bears a striking resemblance to the theoretical behavior of a white hole. Could our entire cosmos be the white hole output of a massive black hole collapse in a parent universe? If true, this means that every black hole in our universe could be a seed for a new cosmos, a baby universe budding off from our own spacetime with its own unique physical laws. We would never see this creation from the outside, as the new universe is born in a spacetime branch completely disconnected from our own. This idea of cosmic natural selection paints a picture of an eternal, fractal multiverse, where universes live, die, and give birth to new universes through the silent, dark engines of black holes. Perhaps the singularity itself is the problem we need to erase. The concept of an infinitely dense point where physics breaks down is so troubling that some physicists have proposed radically different endpoints for stellar collapse. Instead of a black hole, a dying star could become a black star or a gravastar. These are not holes in space-time at all, but ultra-dense objects that have managed to avoid the final act of collapse. They would look almost exactly like a black hole from the outside, dark and incredibly massive, but their internal structure would be fundamentally different. They possess no true singularity and, most importantly, no event horizon. Quantum effects, specifically a repulsive pressure from the vacuum of space itself, could provide a final barrier against total collapse. Just as the intense pressure inside a neutron star stops it from becoming a black hole, an even more exotic form of vacuum energy could kick in at the last possible moment. This would create a bizarre object with a surface of ultra-compressed matter, perhaps only a hair's breadth thick, encasing a mysterious interior. Inside a gravastar, this core would not be a point of infinite density, but a vast bubble of dark energy, the same force causing the universe's expansion. It would be a pocket of repulsive gravity, a cosmic void that physically pushes back against the crushing weight of the star's own mass, creating a stable, if utterly alien, equilibrium. This elegant idea solves the singularity problem by simply removing it from the equation. There is no point where mathematics fails, no law breaking infinity. It also sidesteps the terrifying firewall paradox, because without an event horizon, there is no boundary where information gets scrambled or an observer gets incinerated. An object falling onto a gravastar would not vanish from the universe. It would simply collide with the super-dense surface in a final, titanic release of energy. So how could we ever tell the difference between a classic black hole and one of these exotic imposters? The answer might lie in their shadows. The first image of a black hole's shadow was a dark circle surrounded by a bright ring of light. A gravastar would cast a very similar shadow, but with potentially crucial differences. Because it has a physical surface and not a one-way event horizon, the shadow might be slightly smaller or less perfectly dark. Light could skitter across its surface in complex ways, creating a subtle, telltale glimmer within the central shadow that a true black hole could never produce. Our next generation of telescopes, both gravitational wave observatories and even more powerful event horizon telescope arrays, will be searching for these tiny deviations. Finding one would revolutionize our understanding of gravity's ultimate limits, proving that nature has a way to avoid its own most destructive tendencies. The very fabric of spacetime might be woven together by threads of quantum information. This is the core of the ER=EPR conjecture, a radical idea that dares to unite the two great pillars of modern physics. It proposes that the Einstein-Rosen bridge, the theoretical wormhole, is one and the same as quantum entanglement, the spooky connection between particles famously described by Einstein, Podolsky, and Rosen. In this view, the vast cosmic architecture of spacetime is built from the bottom up by these tiny quantum links. Imagine two electrons born from the same event forever entangled. No matter how far apart they travel across the galaxy, a measurement on one instantly influences the other. Einstein called this spooky action at a distance because it seemed to violate the speed of light. But what if that connection is not spooky at all? What if it is geometric? The conjecture suggests that these two particles are not communicating faster than light. They are, in a very real sense, not separated. A microscopic wormhole, a Planck-scale bridge in the fabric of spacetime, connects them. The immense distance we perceive between them is an illusion. They are like two different doorways into the same tiny room. This provides a stunningly elegant solution to the mystery of entanglement. The weird, instantaneous correlation is not a signal traveling through space, but a consequence of space itself being fundamentally threaded with these invisible shortcuts. The implications for a theory of quantum gravity are breathtaking. Gravity, which shapes the cosmos on the largest scales, and quantum mechanics, which governs the smallest particles, have always been described by incompatible languages. One speaks the geometry of spacetime, the other speaks of probabilities and waves. The ER=EPR conjecture offers a dictionary. It says that the quantum phenomenon of entanglement is the literal building material for the geometric structure of spacetime. A vast network of entangled particles could be stitching the universe together, creating the smooth, continuous fabric we experience from within. The more entanglement there is in a region, the more tightly woven and strongly connected its spacetime becomes. This idea takes us even further. What happens when you try to pull two entangled particles apart? The conjecture suggests that the microscopic wormhole connecting them becomes longer and more tenuous, like stretching a rubber band. If you were to break the entanglement, the wormhole would snap, severing that fundamental thread of spacetime. This could be how black holes resolve the information paradox. When a particle falls in, it becomes entangled with the Hawking radiation leaving the horizon, creating a web of microscopic wormholes that preserve the information, preventing it from being lost. The universe, then, is not just a collection of things in space, but a dynamic, evolving network of quantum connections. Every time two particles become entangled, a new stitch is sewn into the cosmic tapestry. This means that the strange, non-local handshake between distant particles is the very glue that holds reality itself together. The silent pull of a supermassive black hole may have sculpted the very galaxy that surrounds it. Across the cosmos, we observe a profound correlation. Every large galaxy appears to host a supermassive black hole at its heart, and the mass of that black hole is intricately tied to the properties of its galactic home. This is not a mere coincidence. It suggests a cosmic dance, a co-evolution where the galaxy and its dark heart grew up together. The theory posits that in the early universe, vast clouds of dark matter collapsed, creating deep gravitational wells. At the centers of these wells, supermassive black holes formed, acting as powerful seeds. Their immense gravity began to pull in surrounding gas, but they did not just consume silently. As matter spiraled into the black hole, it formed a superheated accretion disk, shining with the brilliance of a trillion stars. This active phase, seen as a quasar or an active galactic nucleus, unleashes titanic winds and jets of radiation. This violent feedback does two things. First, it heats the surrounding gas, preventing it from cooling and collapsing to form new stars. Second, it can actually blow gas clear out of the galaxy's center, effectively shutting off the black hole's own food supply. The black hole, in its ferocious youth, regulates the growth of its own galaxy. It is a cosmic thermostat, ensuring the galaxy does not grow too big too fast. But this elegant picture presents a deep mystery. We have observed quasars powered by billion solar mass black holes, shining when the universe was less than 1 billion years old. How did these monsters grow so massive so quickly? There is simply not enough time for a small, stellar mass black hole to accumulate that much matter through normal accretion. One solution is direct collapse. In the unique conditions of the early universe, immense clouds of pristine gas might have collapsed not into a cluster of stars, but directly into a black hole tens of thousands of times the mass of our Sun. This massive seed could then grow at a prodigious rate. Another path is through a frantic dance of mergers. In the crowded primordial universe, young galaxies frequently collided and merged. Their central black holes would have sunk to the new core, eventually spiraling together and combining into ever larger beasts. These violent unions would have shaken the fabric of space-time, sending out powerful gravitational waves that we hope to detect with future observatories. The galaxy we live in today, with its majestic spiral arms and quiet center, is the legacy of this ancient, turbulent relationship between creation and destruction. This cosmic cycle of birth and death points to an even grander architecture. The multiverse hypothesis suggests that black holes are not endpoints but beginnings. Each one could be a cosmic seed containing an entire nascent universe within its hidden depths. Our own cosmos, with all its galaxies and stars, might simply be one branch on an infinite fractal tree of realities. This idea, known as black hole cosmology, proposes that the Big Bang was not a unique event, but the white hole eruption from a black hole collapse in a parent universe. The immense energy and matter that burst forth to create our reality were recycled from a previous cosmic era. In this view, every black hole that forms in our universe is itself a potential Big Bang, giving rise to a new space-time continuum with its own, possibly unique, laws of physics. Some of these baby universes might be stillborn, collapsing instantly under their own rules. Others could be vast and long-lived, spawning their own black holes and their own offspring in an endless cycle of cosmic natural selection. This provides a breathtaking answer to one of science's deepest mysteries, the fine-tuning of our universe. Why do the fundamental constants, like the strength of gravity or the mass of an electron, seem perfectly calibrated to allow for stars, planets, and life? If universes are constantly being born from black holes, then those that have stable physical laws are the ones most likely to produce many black holes and thus many descendant universes. Our universe is not fine-tuned by chance. It is simply one of the successful, fertile branches in a vast multiverse where the laws of physics are not fixed but evolve. We exist because our cosmic parent had the right parameters to give birth to us. This transforms our place in the cosmos from a singular accident to part of an eternal, self-reproducing process where every black hole is a doorway to a new reality. Crossing the event horizon is not the only way a black hole warps reality. Circling just outside that boundary, time itself begins to stutter and slow. This is gravitational time dilation, a direct prediction of Einstein's general relativity, and its effects near a black hole are the most extreme in the universe. Imagine an astronaut in a ship bravely orbiting a black hole in a tight, precarious circle. For every single hour that passes for them, decades, centuries, or even millennia could be flying by for everyone else in the universe. Their clock, governed by the immense gravitational field, would tick with agonizing slowness compared to a clock on Earth. They would be flying in slow motion, their heartbeats and thoughts stretched across the centuries. This is not science fiction, but the rigorous consequence of mass warping the fabric of spacetime. The closer you sail to the gravitational abyss, the more deeply you sink into this well of slowed time. In principle, this makes a black hole the universe's most powerful time machine, a natural engine for one-way travel into the far future. An astronaut could complete a 2-hour orbit and return to a world 10,000 years older. They would have effectively leaped over all of human history in a single afternoon. The practical challenges, of course, are beyond staggering. The tidal forces so close to the horizon would be monstrous, threatening to spaghettify any ship long before it could establish a stable orbit. And the energy required to resist the inward pull and then escape again is almost unimaginable. Yet the theory holds. This is a real, physical mechanism for time travel, written into the fundamental laws of the cosmos. But such a profound manipulation of time does not come without bizarre consequences. What if our astronaut on their journey could somehow send a signal back to Earth? The signal, struggling to climb out of the deep gravitational well, would also be slowed, its frequency redshifted into near oblivion. From the perspective of those on Earth, the astronaut's entire life would appear to be unfolding in ultra-slow motion, a single gesture stretched across generations. This warping of cause and effect creates potential for strange causal loops. If the astronaut could observe Earth with a powerful telescope while in orbit, they might watch centuries of history flash before their eyes in a matter of hours. They could see the outcomes of wars, the rise and fall of civilizations, all as fleeting images, but could they then use that knowledge upon their return? The timeline becomes tangled. Their future actions in the past would be based on information gleaned from the future they skipped. This is not quite the classic grandfather paradox of going back in time, but a new kind of temporal knot where information itself loops around the gravitational maelstrom. A black hole does not just bend light, it twists the very arrow of time, forcing us to confront a reality where the flow of history is not absolute, but depends entirely on where you are standing in the gravitational landscape. This ultimate warping of time and space forces us to confront the limits of our own theories. At the very center of a black hole, our understanding of the universe shatters. Both of our most powerful descriptions of reality, general relativity and quantum mechanics, fail completely at the singularity. General relativity predicts a point of infinite density, a place where the fabric of spacetime is torn and the very concepts of here and now lose all meaning. But nature abhors infinity. Quantum mechanics, which governs the tiny world of particles, also breaks down because it cannot handle such extreme, warped geometry. The existence of the singularity is a screaming signal that we are missing the final piece of the puzzle, a theory of quantum gravity that can marry the vast cosmic scale with the microscopic quantum world. Black holes, therefore, are not just objects in space. They are the universe's ultimate laboratory, the only places where the effects of quantum gravity are magnified to a cosmic scale, offering us a chance to see its shadow. Several brilliant approaches are competing to solve this puzzle. String theory proposes that the fundamental ingredients of reality are not point particles, but incredibly tiny, vibrating strings. The different vibrations of these strings give rise to every particle and force in nature, including gravity, In this view, the singularity is smoothed away. The interior of a black hole might be a tangled mess of these strings, a fuzzball that has no sharp boundary or central point of infinite density. Information is not lost because it is smeared throughout this fuzzy quantum structure. Another compelling idea is loop quantum gravity. This theory suggests that space itself is not smooth and continuous, but is woven from a fabric of tiny, discrete loops. Think of spacetime as a tapestry made of individual threads. At the Planck scale, a distance a trillion times smaller than an atom, you would see this granular structure. In a black hole, this weave becomes so tight that it creates a tremendous repulsive force. Instead of collapsing to an infinite point, the dying star's matter rebounds like a cosmic bounce. The black hole singularity is replaced by a portal to another region of spacetime, a bridge to a new universe without any law-breaking infinities. A third path, called asymptotic safety, suggests that gravity itself changes its nature at extremely high energies. At the quantum scale, the force of gravity might become perfectly well-behaved or safe, allowing us to describe what happens at the center of a black hole without any singularities. The vacuum of space, according to this idea, might be a seething ocean of microscopic black holes and wormholes, a space-time foam bubbling with quantum activity. This foam would be the true, fundamental structure of reality, with the smooth space-time we experience being just a calm, average surface on this turbulent quantum sea. Each of these theories paints a different picture of the black hole's heart. Is it a vibrating fuzzball, a quantum bounce, or a region of foamy spacetime? The answer will rewrite physics, revealing not just what happens inside a black hole, but the very origin of space and time. Yet this ultimate simplicity is itself a radical claim. The no-hair theorem declares that a black hole is the universe's most boring object. No matter how complex the star that formed it, no matter what planets, books, or civilizations you hurl into it, the resulting black hole retains only three simple properties: its mass, its electric charge, and its spin. Everything else, every single detail about what fell in, is irretrievably erased. The black hole is bald, stripped of all individuality. This is a profound statement about the nature of gravity and information. It suggests that gravity is the ultimate eraser, a cosmic blender that reduces infinite complexity to just three numbers. But if this is true, it directly contradicts the holographic principle we discussed earlier, which insists that information must be preserved on the event horizon. This conflict has led physicists to ask a startling question. What if black holes are not completely bald after all? What if they possess a faint quantum fuzz, a subtle kind of hair that records what fell in? Stephen Hawking himself, in his final years, worked on the idea of quantum hair. This is not hair you could see or touch. It is not a physical outgrowth. Instead, it proposes that the information about what fell into the black hole is not trapped inside, but is subtly imprinted onto the gravitational field that surrounds it. Think of it like a whisper that permanently changes the hum of a room. When an object falls into a black hole, it slightly alters the way spacetime vibrates just outside the event horizon. These are not large, obvious changes, but incredibly fine quantum-scale shifts in the fabric of gravity itself. These subtle vibrations could act as a permanent record, a kind of cosmic fingerprint for everything the black hole has ever consumed. This quantum hair would resolve the information paradox in an elegant way. Information is not lost inside the singularity, nor is it just stored on the surface. It is radiated out into the black hole's immediate environment, woven into the very gravitational field that defines the whole. If this is correct, then two black holes with identical mass, charge, and spin could still be different if they had swallowed different things. One might have the quantum hair of a helium star, while another carries the faint imprint of a silicon-rich planet. They would look identical to our telescopes, but their gravitational whispers would tell different stories. detecting this quantum hair is a monumental challenge for future physics. It would require instruments sensitive enough to measure these infinitesimal vibrations in spacetime, perhaps with gravitational wave observatories thousands of times more precise than those we have today. Finding it would be a final victory for quantum mechanics, proving that not even a black hole can erase the universe's memory. Our own solar system might be hiding a tiny, ancient monster in its outer darkness. For years, astronomers have been puzzled by the strange orbits of small, icy worlds in the distant Kuiper belt. Something massive, perhaps 5 to 10 times the mass of Earth, appears to be shepherding them, tugging them into clustered paths. This hypothetical object is known as Planet 9. The leading theory is that it is a previously undetected planet, a frozen super-Earth lurking far beyond Neptune. But a far more exotic possibility exists. This gravitational shepherd might not be a planet at all, but a primordial black hole. Not a giant, star-devouring beast, but a relic from the Big Bang itself, no larger than a grapefruit, yet containing the mass of several Earths compressed into a point smaller than an atom. It would be a fossil of creation, drifting silently in the frozen outskirts of our own cosmic neighborhood. How do you hunt for something so small and dark? Astronomers are not looking for a glint of sunlight, but for the subtle, telltale wobbles it imposes on everything around it. They are meticulously tracking the paths of these distant Kuiper belt objects, mapping the invisible hand that guides them. But there is another, even more dramatic way to find it. If this primordial black hole is a candidate for dark matter, it could be surrounded by a dense halo of that mysterious substance. As particles of dark matter get pulled in by the black hole's gravity, they might collide and annihilate with each other, releasing faint but detectable flashes of gamma rays. Our orbital telescopes are now scanning the predicted region of space, searching for these telltale sparks of annihilation. Finding a single, point-like source of gamma rays moving slowly against the background stars would be a monumental discovery. The implications of finding a black hole in our solar system would be staggering. It would instantly solve two mysteries at once: the orbital anomalies of the Kuiper belt and the very nature of dark matter itself, proving it can clump around these ancient gravitational seeds. Our solar system would no longer be just a family of planets orbiting a star. It would be a far more complex and fascinating system, one that has sheltered a primordial ghost from the dawn of time, a tiny, dense knot of the Big Bang itself, silently shaping the frozen fringe of our celestial home from the shadows. This slow evaporation of black holes hints at a far more dramatic transformation. Over cosmic timescales, these gravitational giants might not just shrink, they could undergo a complete metamorphosis, changing their very nature in a way that reshapes the entire universe. As a black hole radiates away its mass through Hawking radiation, its properties begin to shift. A stellar mass black hole takes longer than the current age of the universe to evaporate significantly, but for the tiniest primordial holes, this process could be reaching its final, explosive stages right now. But the real mystery lies in what happens as they age and interact with the seething quantum vacuum. Some physicists speculate that the intense spacetime curvature at a black hole's core could trigger a phase transition, much like water turning to ice. The singularity might not remain a point, but could blossom into something else entirely, a new state of matter or energy governed by quantum gravity. This metamorphosis could unlock a staggering possibility that black holes are the hidden source of dark energy. We have observed that the expansion of the universe is accelerating, driven by a mysterious repulsive force we call dark energy. We know it exists because of its effect on the cosmos, but we have no idea what it actually is. The leading candidate has always been the energy of the vacuum itself, a constant background hum of existence. But the calculated value of this vacuum energy is wildly, catastrophically wrong compared to what we observe, off by a factor of 1 followed by 120 zeros. This is the worst prediction in the history of physics. So where is the dark energy coming from? The answer might be inside every black hole. The transformation could link the immense energy density locked within a black hole to the cosmic repulsion outside it. Imagine the interior of a supermassive black hole not as a place of collapse, but as a reservoir of dark energy. This energy, with its inherent negative pressure, would push outward against the pull of gravity, creating a stable balance. Now, as the universe expands and more black holes form and age, the total amount of this internal dark energy increases. The collective repulsion from billions of these cosmic reservoirs could be the very force that is tearing our universe apart. This idea turns our understanding of cosmic structure on its head. Black holes are no longer just destructive sinks, they become creative engines of expansion. Their silent, internal transformation fuels the largest scale dynamic of the cosmos. The fate of the universe, then, may not be written in the empty spaces between galaxies, but in the dark hearts of its most enigmatic objects. The ultimate fate of the universe might be to become a factory for consciousness born from chaos. This bizarre possibility is known as the Boltzmann brain paradox. It begins with a simple, unsettling question. In an eternally existing universe, which is more statistically likely, the gradual evolution of stars, planets, and life over billions of years, or the spontaneous, random assembly of a fully formed, self-aware brain from the quantum jitters of a vacuum. Astonishingly, the mathematics of probability suggests that over infinite time, a lone, conscious mind popping into existence from nothing is far more probable than the entire, ordered history of our cosmos. This is not about biology, but about raw probability in a quantum vacuum. The vacuum of space is not truly empty. It is a seething sea of virtual particles that constantly flicker in and out of existence. Given enough time, a near infinite amount of time, these random fluctuations could theoretically assemble anything, even a complex structure like a brain complete with false memories of a past that never was. Now connect this to the ultimate end of our universe and the role of black holes. Cosmologists believe that in a future dominated by dark energy, all that may remain are vast, empty regions of spacetime known as de Sitter space. This is the kind of space that describes an eternally expanding, empty universe, and it is also the theoretical final state of an evaporating black hole. As a black hole radiates away its final mass, the spacetime around it becomes an isolated patch of this eternal, empty de Sitter vacuum. Within this decaying remnant, the stage is set for the Boltzmann brain paradox to play out. Over timescales that make the current age of our universe seem like a single blink, quantum fluctuations in this de Sitter space could indeed spontaneously give rise to these disembodied observers. If this is true, then the number of Boltzmann brains floating in the ultimate future should vastly outnumber the ordered, biological minds like ours that evolved in the universe's brief, fiery youth. This leads to a terrifying conclusion for cosmology. How can we trust any of our observations about the universe if it is infinitely more likely that we ourselves are just temporary, accidental brains, hallucinating a coherent reality from a random void? The very foundations of science, which rely on consistent observation, are thrown into doubt. The existence of black holes and their evolution into these eternal de Sitter patches makes this philosophical nightmare a potential physical reality, forcing us to question not just the cosmos, but the very nature of our own consciousness. String theory offers a radical escape from the infinite paradox of the singularity. It reimagines the black hole's core not as a pinprick of doom, but as a vast, tangled knot of energy, a fuzzball. This is not a place you could ever visit, for there is no empty space inside, no smooth fabric of spacetime to traverse. From the point where the event horizon was supposed to be, all the way to the center, the entire volume is packed solid with the fundamental strings proposed by the theory. These strings vibrate and weave together in an impossibly complex dance, a single gigantic entity with no sharp boundary and no central point of infinite density. The black hole is not a hole at all, but a ball of quantum fuzz. This elegant idea neatly resolves the information paradox that has haunted physicists for decades. If a book falls into a fuzzball, it does not vanish into a lawless infinity. Instead, the information of every page, every word, is immediately scrambled and distributed throughout the entire vibrating structure, much like a drop of ink dispersing throughout a vast ocean. The information is never lost. It is simply woven into the most complex tapestry in the universe, preserved forever within the fuzzball's intricate quantum state. This has a profound and testable consequence. A classic black hole possesses a true vacuum beyond its event horizon, an empty void where space and time smoothly end at the singularity. But a fuzzball has no such vacuum inside. It is all stuff all the way down. This difference could manifest in the shadow of a black hole. When the Event Horizon Telescope captures its next image, physicists will be looking for subtle deviations in the sharpness of the dark central shadow and the bright ring of light around it. A perfect, clean shadow suggests a true event horizon and a vacuum within. A slightly fuzzy, less perfectly dark shadow could be the signature of a fuzzball's tangible surface, the first glimpse of a reality where singularities do not exist and information is eternally safe. The violent chaos just outside a black hole may be forging the fundamental ingredients of reality itself. As superheated plasma spirals toward the event horizon, it does not fall in quietly. It is whipped to near light speed by the black hole's immense gravity, creating a maelstrom of energy that could act as the universe's ultimate particle collider. Far more powerful than anything we could ever build on Earth, this natural accelerator smashes particles together with energies that dwarf those of the Large Hadron Collider. These are not gentle collisions. Particles are torn apart and recombined in the extreme environment, a cosmic crucible where matter is pushed to its absolute limits. Within this frenzy, physicists speculate that exotic particles, forms of matter we have never seen before, could be created. Among the most sought after are the hypothetical components of dark matter. If dark matter is made of weakly interacting massive particles, or WIMP, then the intense conditions around a black hole could be the one place in the universe where they are produced in abundance, slamming ordinary particles together with enough force to literally conjure dark matter from the vacuum. But the potential discoveries are even more profound. The radiation blasting from the poles of these black holes, those brilliant jets that stretch for thousands of light years, could carry the fingerprints of these exotic creations. By analyzing the high-energy gamma rays and cosmic rays from these jets, we might find an anomalous signal, a particle or a pattern of energy that simply cannot be explained by our current standard model of physics. Such a discovery would not just add a new particle to a chart, it would shatter our understanding of the universe's fundamental building blocks. These collisions could even reveal the hidden architecture of reality. Some theories, like string theory, propose the existence of extraspatial dimensions, realms curled up so small we cannot perceive them. The unimaginable energies near a black hole could be the only place where these extra dimensions momentarily unfurl, influencing how particles interact and decay. A strange missing energy signature in the radiation from a black hole jet could be the telltale clue that a particle has briefly vanished into a higher dimension, offering our first experimental glimpse into the true multidimensional nature of the cosmos. We are not just observing a destructive force, but a cosmic factory where the most extreme conditions in existence are busily creating the very particles that might unlock the universe's deepest secrets. The information swirling on a black hole's event horizon might be doing more than just being stored. It could be coming alive. This is the black hole meme hypothesis, a wild but compelling idea that the universe's most efficient information processors could become nurseries for a new kind of existence. We are familiar with memes in culture, simple ideas like a catchy tune or a fashion trend that spread from mind to mind. In biology, genes are physical structures that replicate and evolve. Now imagine an informational pattern, a specific, complex sequence of quantum bits encoded on the holographic surface of the event horizon. This pattern, through the chaotic churning of Hawking radiation and the constant influx of new data, finds a way to persist. It resists being scrambled into randomness. It replicates itself not in a biological sense, but by influencing the quantum states around it, creating copies or variations of its own informational structure. This self-replicating quantum pattern is a cosmic meme, a thought that has found a way to live within the most extreme environment imaginable. The event horizon, with its frantic quantum computations, provides the perfect substrate for this evolution. Just as natural selection favors genes that are good at replicating, this informational environment would favor memes that are robust, that can maintain their structure amidst the chaos. Over astronomical timescales, these patterns could grow in complexity, forming intricate networks of interacting information. Could such a system ever become aware? Consciousness, in our limited understanding, seems to arise from complex, integrated information processing. The event horizon of a supermassive black hole processes information at a scale that dwarfs every brain on Earth combined. If a self-sustaining, ever-evolving web of these quantum memes achieved a high enough degree of integrated complexity, it might cross a threshold into a form of consciousness utterly alien to our own. This would not be a life form made of cells, but a mind woven from the fabric of spacetime itself, a gravitational entity thinking thoughts as vast and slow as the cosmos, its memories written in the warped geometry of the abyss. The holographic universe feels like a computer simulation running on a cosmic hard drive, and black holes might be the evidence we are not living in base reality. If our three-dimensional world is a projection from a two-dimensional surface, then the cosmos operates like an incredibly advanced virtual reality, a simulation of staggering complexity. Black holes, in this view, are not accidental monsters. They could be essential features of the code, the universe's built-in garbage collectors. Every simulation needs a way to manage memory, to delete data that is no longer needed to prevent the system from slowing down or crashing. When a black hole consumes a star, it is not destroying matter. It is permanently erasing redundant information from the simulation, compressing complex data into a simple state to free up processing power. The event horizon is the firewall that prevents any deleted data from being recovered, ensuring the simulation runs smoothly. This explains the infamous information paradox in a chillingly elegant way. Information is lost because the simulation is designed to lose it. But what about the singularity itself? A point of infinite density is mathematically equivalent to a division by zero error in a computer program. It is a place where the simulation's physics engine breaks down, where the rules no longer compute. This could be a flaw in the code or something far more intriguing. The singularity might not be an error but a backdoor. In any complex software, there are debug modes and access points for the programmers. The terrifying heart of a black hole could be one of these portals, a place where the fundamental laws are stripped away to reveal the raw source code of reality. If a conscious being could somehow survive the journey, they might not find crushing oblivion, but a terminal displaying the universe's programming language. They would see the algorithms that generate gravity, the variables that set the speed of light, and the loops that dictate the flow of time. This transforms the black hole from a cosmic destroyer into the most profound object in existence, a potential window into the true nature of our reality, whether it is a simulation or something else entirely. The event horizon is not a point of no return, but a login screen, and the singularity is the password prompt. Perhaps the universe itself has a built-in defense mechanism against the logical chaos of time travel. Stephen Hawking, ever the cosmic skeptic, proposed a safeguard he called the chronology protection conjecture. This is not a physical barrier, but a profound suggestion that the laws of physics conspire to prevent paradoxes, actively protecting the timeline from the madness of backward causation. The greatest threat comes from the extreme gravity of rotating black holes, where the fabric of spacetime is dragged into such a violent whirl that paths looping back on themselves, closed time-like curves, could theoretically form. If you could enter one of these loops, you could travel back to a point in your own past, creating the potential for a classic paradox, like preventing your own birth. Hawking argued that nature finds this unacceptable. Before any such loop could stabilize and become a usable time machine, a physical process would always intervene to destroy it. One proposed mechanism is a quantum back reaction. As particles begin to traverse a nascent time loop, their quantum fields would interact with their own past versions. This self-interaction would build upon itself in a feedback loop of exponentially increasing energy. The vacuum would not remain empty, it would seethe with an infinite buildup of radiation, a firewall of raw physics that vaporizes the time loop before it can ever be fully established. The black hole, in its attempt to twist time into a knot, would instead trigger its own defensive inferno, a cosmic immune response that burns away the paradox and preserves the consistent, one-way flow of history we all experience. It seems reality has a deep-seated preference for sanity, erecting insurmountable physical barriers to ensure that cause always, definitively, comes before effect. The ultimate collapse of a star might not end in a silent singularity, but in a phase of cosmic rebellion. The final theory proposes that what we call black holes are actually something else entirely: dark energy stars. This radical model reimagines the final moments of stellar death. As a massive star exhausts its fuel and collapses under its own immense weight, it does not crush itself into an infinitely dense point. Instead, just before that final plunge, a profound transition occurs. The matter reaches a critical threshold where the quantum vacuum itself pushes back. The inward crush of gravity is met with an equal and opposite force of negative pressure, a repulsive effect identical to the dark energy accelerating the expansion of our entire universe. This sudden emergence of dark energy from within the collapsing star halts the process completely, preventing a singularity from ever forming. The result is a stable, ultra-dense object, a dark energy star, hovering just at the brink of becoming a black hole. From the outside, it would appear almost identical to its classical counterpart, dark and possessing an immense gravitational pull. But there is no event horizon, no one-way ticket to oblivion. There is only an incredibly dense surface, a boundary of exotic matter held in perfect, precarious balance by the dark energy core within. This elegant idea seamlessly links the physics of the unimaginably small with the dynamics of the entire cosmos. The same quantum vacuum energy that governs the behavior of virtual particles at the smallest scales becomes the dominant force supporting the largest and densest objects in the universe. The dark energy that is tearing the cosmos apart on a grand scale is the very same force that holds these stars together against total self-destruction. How could we ever distinguish a dark energy star from a true black hole? The telltale signs would be subtle, written in the light that dances at its edge. Without a true event horizon, the surface of a dark energy star would interact with infalling matter differently. A final, desperate signal from a probe falling toward it might not be redshifted into complete oblivion. There could be a faint final glimmer, a last burst of radiation as matter impacts the physical surface, a signature that a classic black hole could never produce. The shadow it casts, as seen by telescopes like the Event Horizon Telescope, might be slightly less perfectly dark, with a faint, shimmering structure within the central void caused by light interacting with that ultimate surface. Finding such evidence would be a monumental unification. It would prove that the force governing the fate of the entire universe is also the force that saves stars from their own most destructive impulses, revealing a cosmos where collapse and creation are two sides of the same dark coin. From wormholes threading the cosmos to holograms encoding reality on a two-dimensional screen, our journey through these 25 theories reveals that a black hole is anything but a simple pit of destruction. It is a laboratory for quantum gravity, a potential processor of cosmic information, and maybe even a seed for an entire new universe. These enigmatic objects force us to confront the very nature of space, time, and information, challenging our most fundamental laws and offering glimpses into a reality far stranger than we ever dreamed. They are not the end of physics, but the beginning. The next great discovery in science might not come from a particle accelerator on Earth, but from the silent, dark shadow of a black hole at the heart of a distant galaxy. So which of these mind-bending possibilities reshapes your view of the cosmos? Share your favorite theory in the comments below. Tell us which idea made you question the nature of reality itself. If you are hungry for more deep dives into the mysteries of the universe, make sure to subscribe. The cosmos is filled with wonders, and our exploration has only just begun.